Okay, and we'll talk about Poisson distribution as I promised earlier. We'll have a little bit more detailed discussion about that, and we'll see how the Bayes rule allows us to make decisions about how to place bets on the EPL games. EPL stands for English Premier League, so that's the highest division of the soccer league in England. And you have multiple betting companies where you can place your bet. So those are your bookies. And then you have multiple teams you can bet on, and different bookies will give you slightly different odds of this team winning the EPL. And the question is, if I want to place a bet, how do I make this decision based on the historical data? And we will calculate odds of possible match outcomes 0-0, 1-0, and usually in soccer you don't go above 4 or 5. Anyhow, so let's say we have Arsenal Liverpool game, and we have two random variables. The first random variable X is the goals scored by Arsenal, and Y is goals scored by the Liverpool. And if we want to calculate the probability that Arsenal wins, then we need to have probability that X greater than Y, and probability of a draw is just probability that those two variables equal to each other. And let's take we use historical data, and historical data has something like this. It has the home team, and then away team, and then outcome. So let's say you have Arsenal versus the Liverpool, and the outcome was 0-1. And then when Arsenal played away and Liverpool was the home team, the outcome was 2-1, something like that. So what we're gonna do, we're gonna take this historical data, so that's the data set that we have, and we're gonna assume that both of them, X follows the Poisson distribution, and Poisson distribution parameterized by the rate parameter lambda. So lambda for the Arsenal. So Arsenal will have its own average rate of goals, and Y is also Poisson, and average rate of goals by the Liverpool. And I'm gonna calculate lambda A and lambda L from data. So I just gonna use maximum likelihood estimation in this case. So I just gonna lambda A, I gonna sum all of the scores. So let's say I have I goes from 1 to N. So let's say for Arsenal, I want to calculate NA. So NA is the number of games played by the Arsenal, and I gonna sum up the number of the scores. So scores or goals scored by the Arsenal in each of those games, and then I just average it out. And the same way I calculate lambda for the Liverpool, and let's say I calculate it for Arsenal and it happens to be 0.6, and for the Liverpool it's 1.4. And then I just gonna do Monte Carlo simulations here, something we talked about. I'm gonna generate 100 random draws from the Poisson distribution that describes the Arsenal outcomes, and then the Poisson distribution that describes the Liverpool outcomes. And then I just gonna calculate in how many cases what was the proportion of the games where Z2 was less than Z1 was less than Z2, meaning that Arsenal lost the game, and vice versa. I'm gonna calculate the draw by calculating in how many cases or proportion of the cases when the scores was equal. And again, this is how historical data looks like, and I use this data to calculate my rates lambda. Here I'm just using maximum likelihood estimation. And here are my models, and here how well those models match the data. And what you see here, the turquoise color is my model predicted outcome, and the orange color is the actually observed outcomes in the data. And you see that for at least for Chelsea here, the model does pretty good job. It correctly predicts the proportion of 0 goals, and for 1 goals it actually slightly overestimate, and for the 2 goals it's actually slightly underestimate. Okay, and the same we see for the so actually this one is for Arsenal. So Arsenal was 0.6. It's incorrect label here. So it's Arsenal. And this is Chelsea. This is correct. So the same we see for the Chelsea. Chelsea lambda was slightly high, so we go all the way to 5 goals here, and it's actually we see pretty good match here and here. We see that model slightly underestimates for 3 goals. It does pretty good job for 2 goals, and for 1 goal, and for 0 goals it slightly overestimate the probability of that outcome. So, but in general, model seems to be reasonable. It does a reasonable job explaining the outcomes, the number of goals scored by each of the teams. And now we actually want to improve this model. So just instead of calculating those maximum likelihood estimates for the parameters lambda, we want to account also for the interaction between 2 teams. So if one team has good defense and another team is good offense, then this interaction tells us that the outcome of the game is going to be relatively low number of goals scored. Even though you have a good scoring team, if they play against the team that has good defense, then they will have hard time scoring against the team. So here's what we're gonna do. We actually gonna calculate 2 parameters. We're gonna calculate the parameter that models the strength of the attack of the team, and then defense weakness of the team. And instead of just using the average number of the goals, we're gonna combine those 2 pieces of information together. And this is not the true Bayesian approach, but it's basically that's the spirit of the Bayesian approach. And I'm sure you can come up with priors so that will be equivalent to this type of approach. But anyhow, so the way we're gonna calculate it, we're gonna start with our original lambda. So let's say we're gonna model Manchester United versus Hull. So 147 is the average number of goals by Manchester United. And then we multiply, so Manchester United plays the Hull, so then we multiply by the strength of the Manchester United. So Manchester United has the strength of 146, and then we multiply by the weakness of the opponent, which is Hull, 137. And then we get this adjusted number 2.95. And so this is the number of goals we expect Manchester United to score when they play against the Hull. And we do the same for the Hull. Let's say Hull is also average number of goals is 147, but the attack strength is not as good of Hull as of Manchester United. And Manchester United has very good defense, so the defense weakness is only 0.52. So 0.65 is the number of goals we would expect Hull to score against Manchester United in this game. And again, we're gonna do the simulations, and we're gonna use the new values of lambda. So this is lambda for the Manchester United, and this is lambda for the Hull City, and this is the expected number of the goals. And in my simulations, there was 7 times Manchester United scored 0 goals, and 49 times Hull scored 0 goals, and 1 goal was scored in 22 cases by Manchester, and the 41 cases by Hull City. So that's the outcome of my simulation. And of course my model is only as good as prediction, and in my simulation Manchester United wins 88 times out of 100. So if I'm to place a bet according to this model, then I should place the bet whenever odds are below the 88 to 100. And my model predicted the most likely outcome is 0-3, 12 games out of 100 end up with this score. The actual outcome was 0-1. They played on August 27, 2016. And in my simulation, 0-1 was the fourth most probable outcome. So it looks like my model did a reasonable job. My model predicted the winner, and it predicted the actual outcome of the game with relatively well. But the main point here, why we're talking about this is this point is the way that you adjust this parameter lambda and you incorporate additional pieces of information. So you take the average lambda across all of the games by Manchester United, and then you actually take additional piece of information, the strength of the Manchester United and the weakness of the whole, and you adjust this lambda by just multiplying those three factors together to calculate the new value of the average or expected number of the goals to be scored by this team. And this is the same approach, by the way, Nate Silver used a very similar Nate Silver used when he nailed prediction of the both of the Obama elections. And the way he did that, he took the results of the polls, so the surveys, and then he took the probabilities of each candidate winning according to the surveys, and then he adjusted those probabilities and he called it his secret sauce. So his secret sauce was those adjustment factors. He basically tried to identify inefficiencies or the ways in which those surveys were incorrectly conducted, and then he converted those incorrect ways of conducting service into the adjustment factors. So he basically knew how to properly adjust the results of the surveys in each of the states conducted by different surveying companies to calculate the correct probability of a candidate winning. And the adjustment was in this fashion. He basically would take the one that was calculated by the survey, and then he updated it. So you can think of it as a base rule in the Manchester United case. So we have our prior assumption, lambda for Manchester United is 1.47. So that's what we calculated from the data, and you can think of it as empirical Bayesian prior on what is the rate is going to be. And then we say, okay, but we have two additional pieces of evidence. We know that Manchester United is very strong on the attack, and we also know that Hull is weak in the defense. And so we calculate the posterior by just calculating the product of those three numbers.